Again, welcome everybody, and thank you for joining us on today's webinar, The Natural Gas Coriolis Measurement Revolution. I'm Allison Sterling, Marketing Manager at Emerson Micromotion, and I'm pleased to welcome you to the Emerson Flow Expert webinar series. Before we begin today, I'd like to take just a brief moment to acquaint you with your webinar environment. On your screen, you should see a presentation window on the left side, a Q&A chat window in the upper right-hand corner, media player controls, and a resource box for the related content where you can review and download content during the event. You can also resize, move, or minimize any of these windows that are in that console during the event to fit your viewing preferences. And you'll also notice at the bottom of your display that you should have a row of icons that give you added capabilities where you can share this webinar via social media channels or even request a visit from one of our Flow experts. Throughout the presentation today, we encourage you to interact with our speaker by typing in questions using that chat panel. We will be answering questions both live during the event as well as after the presentation. And I'd also like to note that at the end of the presentation, a survey window will pop up at the end of the webinar where we'd love for you to provide us feedback so that we can optimize future webinars. We are also recording today's webinar, and we will make a link to this recording available to you 24 hours post-event via email so that you can either view it again or share it with your colleagues. And on today's webinar, we are lucky enough to have joining us Marc Buttler, the Oil and Gas Midstream Industry Manager with Emerson Micromotion. Marc is responsible for representing customer needs for oil and gas pipeline, gas processing, and terminal applications. During his 25-plus years with Emerson Process Management, Marc has held a variety of manufacturing, engineering, and global marketing positions. Marc has also worked as a physical scientist at the National Institute of Standards and Technology, or NIST, and he holds a BS degree in mechanical engineering from the University of Colorado. Welcome, Marc. Thank you so much for joining us.
Well, thank you, Allison, and I also want to thank everyone who's joined us today. Thank you all for taking time out. During this webinar, we will cover how important measurement is to the confidence between parties that trade in natural gas, as well as how important it is in maintaining the prosperity of everyone involved. And so the webinar will start with a short summary of the basics on how a Coriolis meter works to measure natural gas. This section will cover how direct mass flow measurement translates easily into the industry standard units for energy and standard volume. And then we will share how Coriolis meters can help to address many of the concerns and challenges being faced by the industry today in a variety of applications. Many different calibration options are possible with Micromotion Coriolis meters, so we have included sections to cover the most important things to consider when choosing between calibration options, as well as a section on how to preserve your investments in both the meter and in any additional calibration by following best practices in field verification and diagnostics monitoring. We will pause a couple of times during this webinar to ask you, the audience, to weigh in with your thoughts and ideas. So I'm looking forward to everybody's participation there. We'll start by identifying some of the challenges and concerns being faced by the natural gas industry today. The natural gas transmission and distribution industry faces many unique challenges in today's environment. In custody transfer, quality is measured by the accuracy and traceability of the measurements that are used for billing and invoicing. Maintaining accurate measurement is also very critical to protecting profits by achieving good network system balance and reducing prior period adjustments and reconciliation costs. As demand for natural gas continues to rise, new technologies like Coriolis meters are increasingly chosen to meet the challenging need for greater and greater measurement accuracy with less maintenance and cost. As the natural gas transportation infrastructure continues to build out, attention to safety and environmental protections has been increasing, especially in and around high-density population centers. Superior measurement and process control can play a large role in keeping down the costs of compliance with health, safety, security, and environmental policies and regulations. Gas has to keep flowing in many instances to meet contractual line pack commitments and to avoid the safety issues that would arise if the flow of gas were to be cut off. For this reason, availability and continuous functioning of measuring instruments is crucial in order to avoid the unpleasant consequences that occur when a meter stops working and gas has to be allowed to flow by the meter unmeasured. Most rotary meters today deal with this potential safety issue by building in an emergency bypass around the metering chamber that will open whenever the meter mechanical component seizes because of particle contamination in the flow stream, but this allows the gas to pass by unmetered. The cost of calibrating and maintaining measuring devices is becoming a more significant concern as the sheer number of devices increases. In addition to the upfront costs of initial calibrations, the interval that calibration is required and recalibration after that, and the associated costs will also depend on the measuring technology that's chosen and placed into service. As a large portion of the knowledge and expertise in the workforce is nearing retirement age, it is becoming more and more important for operators and suppliers to work together to create and deploy technology that will effectively meet the needs of the future without the need for the in-depth knowledge and experience that has been required to deal with the complex technologies that were used in the past. As more and more sources of supply and uses for natural gas and its components emerge, the increasing variability of composition brings new challenges to accurate measurement for the technologies used previously. This includes the increasing probability that gas may dip below the dew point and liquids may condense, forming wet gas. It also means natural gas professionals now face a growing challenge in order to accurately measure a very valuable liquid commodity represented by the natural gas liquids, or NGLs, that have become the primary source of payment for services provided at the treatment facilities. Good mass flow measurement is crucial in actually determining the NGL custody transfer quantities that can also help dramatically with the complex task of leak detection on NGL pipelines. So I'd like to pause now and take one of the first polls that we have. The poll question will help Emerson to keep our attention focused on addressing your greatest challenges as we head into the future. So please select the answer that indicates your view of the greatest challenge you face or expect to face in the future, and then submit your answer by clicking on the Submit button. We will review the results together when you are all done. Please begin. Okay, we're starting to see some results here, and when it seems to stabilize, I'll go ahead and show everyone the results we're getting. Okay. It looks like the winner in terms of the most responses is changing conditions. So composition, flow rate, pressure, temperature, all of these can affect measurement if they're not well addressed. Everybody at least chose one of the different options. So it looks like we all understand that there's a range of challenges facing us. But this challenge of changing conditions is clearly the one that's concerning most of the people on the webinar today. So that's good because some of the information we'll cover a little bit later on does get directly into this subject. So with Emerson as your measuring partner, you'll join the revolution that's taking place in the industry as the industry adopts new methods and technology to meet the challenges of the future. You'll experience new possibilities for greater system accuracy. You'll be able to reduce the cost of real estate and equipment by eliminating the need for long conditioning runs. You'll no longer be subject to additional errors and uncertainty associated with the ancillary pressure and temperature measurements that were needed with other technologies in order to correct for the changing conditions and how those conditions cause the gas to expand and contract. You will enjoy quicker and simpler installation and startup of the metering runs that will then require little or no ongoing maintenance after they're started. And you'll find it easier to meet compliance requirements with equipment that is extremely reliable and that comes with predictive diagnostics and substantial data and audit trail recording capabilities. Now I will explain how a Coriolis meter works. Inside the Coriolis meter, there are several different components, and I'll start with those. The heart of the Coriolis meter is a pair of vibrating tubes, sometimes called the flow tubes, that you see in this view of the meter that shows how the flow entering the meter is split and diverted into the flow tubes. As the fluid later nears the end of the meter, the flow from the flow tubes is merged back together and discharged back into the pipeline. So there is a drive coil, and that is a magnet pair, as shown here, to apply a small amount of additional force that's needed to keep the tubes vibrating at exactly the right distance apart. The magnet is mounted on one tube, and the coil is directly opposite that magnet on the other tube. And when current is passed through the drive coil, the needed force is applied to push the tubes apart and keep them vibrating, as you see here. There are two additional coil magnet pairs called pickoff coils located on either side of the meter flow tubes, as shown here in this top-down view. These are different from the drive coil in that their purpose is to measure the movement of the tubes, not to push on the tubes. So when there's no flow passing through the meter, the flow tubes vibrate normally, and the tubes are always vibrating, whether there's flow through the meter or not. The electronic transmitter is measuring the movement of the tubes in the two places where the pickoff coils are, and they're generating sine waves. When there is no flow through the meter, these two sine waves are in sync and will lay on top of each other while the tubes are vibrating normally. When the flow starts to pass through the meter, the flow tubes begin to twist, as you can see in this view to the right. The electronic sees this twisting as a shift in the phase or time delay between the signals coming from the two pickoff coils, and we have a mass flow measurement. The mathematics of the signal processing is very simple. The mass flow rate is exactly proportional to the amount of phase or time delay measured between the two pickoff coils, and this makes calibration of the meter relatively easy because all it is necessary is to find the single flow calibration factor at any one flow rate and then apply that same factor to the phase shift that's measured at any other flow rate to arrive at a correct flow measurement. Coriolis meters are extremely linear in this regard. One final note on the physics of Coriolis meters before we move on to talk about how they are used to measure natural gas. The geometry of the flow tube design is very important. The twisting motion is caused by Coriolis forces that are due to the flow through the flow tubes, and the farther out and then back that the fluid travels away from the center line of the pipeline, the more raw Coriolis flow measurement signal will be physically generated and measured by the twisting of the flow tubes. This is important when you stop and compare flow meters for gas measurement and when you hope to choose the type of meter that will give you the best accuracy for custody transfer. Because raw sensitivity of any Coriolis flow meter depends on how far out the tube geometry extends from the central axis of the pipeline. The chart shows an actual comparison of this relatively raw signal between meters with large, tall flow tube geometry like Micromotion Elite meters and meters with shorter or medium-sized tube geometry like Micromotion F-Series meters. Signal-to-noise ratio of any Coriolis meter will depend on two things. First and foremost, the signal-to-noise ratio will be higher when the raw sensitivity is higher. The stability of the meter signal when the meter is at zero flow will also impact the signal-to-noise ratio. When the stability is better, the noise is lower, and the ratio of signal-to-noise will again see an increase. Signal-to-noise ratio is very important because a higher ratio makes it possible for a meter to measure with better precision and accuracy. Higher signal-to-noise ratio also opens the door to many other benefits such as advanced diagnostic, calibration fluid flexibility, and greater resistance to adverse secondary effects due to changing process and ambient conditions. We talked about during the poll how important that is to many of you who see changing conditions as one of the biggest challenges. So tube geometry is very important when you're trying to deal with that as a challenge. Now let's finish up this discussion on how Coriolis meters work by turning our attention directly to gas flow measurement. The industry standard practices for trading in natural gas are based on units of standard volume and energy. On this slide, I will refer to standard volume as SCF, which is an abbreviation for standard cubic feet. Standard volume is the volume of a fixed quantity of gas when it is at reference conditions. It is necessary to work in units of standard volume instead of actual volume because the actual volume of a fixed amount of gas will change dramatically as actual pressure and temperature are changing. To get to energy units, a gas chromatograph or other method is needed to measure the heating value of the natural gas. The heating value will vary with changing composition. The heating value can either be represented as energy units per unit of standard volume, such as BTU per standard cubic feet, or as energy units per unit of mass, such as BTUs per pound mass. The simplest and most accurate path to energy flow units is to multiply the mass flow of the heating value expressed in energy units per unit of mass, and you're left with units of energy flow. However, if you have the need to work with heating values defined in units of energy per unit of standard volume, it is easy to make the conversion from mass to standard volume, as we are about to see, and then multiply by the heating value. On this slide are shown three different equations for the conversion from mass to standard volume, or SCF. All three are essentially the same relationship. However, they each show this relationship in different terms that can be found within the AGA standards. American Gas Association publishes these standards, and they help us by providing equations such as these. The equation at the top shows the relationship in the simplest terms. The standard volume at reference conditions is just the mass divided by base density, or the density of the gas at reference conditions. Note that base density is not the same as actual density, but rather it is a fixed constant that will not change unless the composition of the gas changes. Actual density will change just as actual volume will change when actual pressure and temperature are changing. In contrast, base density will not change due to changes in actual pressure and temperature. To see this relationship in some example units, you can find the equation shown here where you can divide by the mass flow rate in pounds per day by base density in pounds per cubic feet, and you're left with cubic feet per day, units of standard volume flow rate. The second equation shows the relationship in terms of the non-ideal gas law as described in AGA 8. And the third equation shows the relationship in terms of specific gravity. Many of the terms in the second and third equations are fixed constants that will never change. These include the pressure and temperature at reference conditions, P sub B and T sub B, as well as the gas constant R and the density of air at reference conditions. Note that the molar weight, the compressibility at base conditions, and the specific gravity of the gas are all values that are determined entirely by the composition of the gas. They do not change as the actual pressure and temperature change. In fact, even as changes in composition do occur, the compressibility at base conditions Z sub B will only change very slightly, about 0.02% as a result. So to recap, when the flow is measured directly by mass with a Coriolis meter, it is still necessary to know the composition in order to convert to either energy or standard volume, but it is never necessary to know the actual pressure or temperature to convert units to base conditions because the mass of a fixed quantity or amount of gas will never change, even when the actual pressure and temperature are changing. There is no other measurement technology for which the energy and standard volume calculations are this simplistic. There are many great places in the natural gas transportation industry to use Coriolis meters. Coriolis meters are a natural fit for custody transfer measurement because of the high potential for accuracy from each individual Coriolis meter. Coriolis meters remain accurate over extended periods of time and under varying conditions, so Coriolis meters are good to help achieve the goals of both equitable custody transfer and good system balance. We will cover the subject of balance in a little more detail later on, However, it's important to note that the larger the Coriolis meter is, the more it's successfully used in transmission applications where capacity is higher and the flow rates are relatively stable, and good accuracy is paramount to maintain system balance. On the other hand, smaller Coriolis meters are often very good at meeting the needs for accurate measurement in city and industry gate applications that require a wide range of flow rates because of the wide variations in demand as seasons and conditions change. So as natural gas liquids become an ever larger part of the natural gas economy, the versatility of Coriolis meters to handle both gas and liquid flow becomes very important. The ability of Coriolis meters to measure in mass units is also very important for NGLs because the composition of NGLs is such that there are no good standard tables for correcting the volume of NGLs back to reference pressure and temperature like there are for gas, crude oil, and other refined products. This is because the possible range of NGL mixture compositions is so vast that it would be impossible to derive a complete set of volume correction factors that would cover all the possible NGL compositions over a practical range of varying pressures and temperatures. Custody transfer of NGL in mass units is hence becoming an increasingly popular solution to this problem. Measuring gas for allocation purposes at the wellhead and separator is also a good opportunity for Coriolis meters. Their ability to withstand two-phase flow disturbances without being damaged and the long-term stability of their calibration are very valuable in some of the remote locations where gas is being produced. Similarly, Coriolis meters perform very well in gas gathering systems because of their ability to measure accurately with dirty and sometimes wet gas flowing through them. Natural gas cavern storage is another good application for Coriolis meters for many of the same reasons mentioned earlier for custody transfer, but also because the meters work in a bidirectional fashion that cuts down on the amount of piping and valves needed. Coriolis meters are a good way to manage buyback of residual gas for treatment plants when fluctuations in supply and demand cause the plant to need to pull back some gas for ramping back up to capacity. By using direct mass flow measurement as an input to the air-fuel ratio control on a compressor or a fire heater, it is possible to use fuel gas with highly variable composition and still maintain huge reductions in emissions and fuel consumption. This can add a secondary benefit of reduced energy costs by potentially eliminating the need to install electric or dual-fuel compression engines that would otherwise be required to stay below emission caps. Finally, there are opportunities for Coriolis meters in the measurement and control of the liquids circulating in the dehydration and amine units of gas treatment plants because of the potential benefits of improved efficiency and reduced emissions that can be gained from those units. I'm going to share just 4 of these example applications in more detail before we move on, starting with custody transfer. The benefits of using Coriolis meters in custody transfer of natural gas include the fact that there is no need for flow conditioning with a Coriolis meter. Micromotion meters have an online diagnostic to check the meter that I will cover in more detail later, and they are not vulnerable to damage by flowing at too high a flow rate. As we discussed, there is no need for temperature or pressure measurement devices to convert back to standard volume units. Some typical results we have seen in applications where micromotion meters are used in natural gas custody transfer include agreement between the pay and check meter of 0.1% for a period lasting over 10 years, and the reductions in capital expenses during installation of over $100,000 because of the costs that were avoided since there's no flow conditioning required. In another example, where micromotion meters have been used to measure gas flowing in and out of cavern storage facilities, operators have experienced the ability to detect water coning and carbon dioxide breakthrough using the same meters that are giving them a highly accurate flow measurement. This is an excellent example of how Coriolis meters give you diagnostic tools not only to assess the health of the meter, but also to diagnose problems in the overall process. Because a micromotion Coriolis meter can measure accurately with flow in either the forward or the reverse direction, they can be used to measure flow in and out of the reservoir without costly additional piping and valves that would be needed to change the direction for other types of flow meters. Overall, because the meters are able to measure accurately with essentially no need for maintenance under tough conditions on dirty gas, operating expenses have been reduced in some cases by up to 80%. Another example is shown in these photos that illustrate how some customers have retrofit Coriolis meters into the buyback lines that are used to take residual gas back into the gas treatment plant when it's needed after a turndown to get the plant back up to capacity. With a Coriolis meter in these lines, the treatment plant has experienced improvements in accounting on produced gas as well as in the mass balance of the plant overall. So we've talked about the importance of maintenance and maintaining good system balance. Let's take a look at how individual meters can impact system balance and also consider what system balance can tell us about the accuracy of individual meters at the same time. This equation shows us how the uncertainty of each individual meter in a system are combined to determine the overall uncertainty of the system. All of the meters flowing into a pipeline network should be considered together to determine a single overall uncertainty of the system influx. And then the process should be repeated to combine all the outflowing meter uncertainties into a single overall uncertainty of the system outflow. These two values, the inflow and the outflow uncertainties, can then be combined as shown in the second equation to estimate the overall uncertainty of the system balance. The larger this uncertainty is allowed to be, the greater the potential is for losses in the system that would be the direct result of nothing other than measurement error. This exercise revealed some interesting conclusions. The more individual meters there are in a system, the better the overall uncertainty will be because there is less impact on the system uncertainty added by each individual meter as a percentage of the overall system uncertainty. Despite that, the overall uncertainty is still improved by using meters that are each individually more accurate. The best balance is achieved when the most accurate meters are used for the highest flow rate streams in the system. The second equation shows that the overall uncertainty of the balance will always be worse than either the uncertainty of just the influx or the uncertainty of just the outflow. And the best way to measure the system throughput is to either look at just the total inflow or just the total outflow. Since you have to determine the overall uncertainties of both of these independently using the first equation, you can then compare them and choose the one that has the smaller uncertainty as your measurement of the throughput. Finally, a good system balance does not assure that each individual meter is measuring accurately. Consider that it's possible for one or more of the meters to be unacceptably inaccurate by itself, and yet the system balance might still have only a small error, either because the contribution of the individual meter is only a very small percentage of the overall flow of the system, or because there are equally bad errors in the opposite direction by other meters in the system that offset the error of the first meter. It is very important to keep this in mind when you consider the importance of each individual meter's accuracy to the parties that are transferring ownership of gas through that one meter. And as the fourth and final example, I want to share how adding a micromotion meter to the line feeding fuel to a compressor engine has delivered some significant benefits. By controlling the fuel intake before combustion occurs with a measurement in mass flow units instead of in standard volume units, the engine runs much more efficiently and with dramatic reduced emissions. This is because controlling in mass units makes the combustion efficiency much less susceptible to degradation as the fuel composition changes. The benefits of this approach are threefold: a reduction of up to 33% in fuel consumption, dramatically reduced emissions, including a 99% reduction in carbon monoxide, and an ability to use fuel gas with variable composition that gives the plant flexibility in where they take their fuel gas from. Bear in mind that the ability to reduce emissions by this much can mean the difference between whether a plant can use fuel gas or will be forced to switch to more expensive electrical power for running compression in areas where permit limits on emissions are tight. It's worth digging into the details of just why combustion control with mass flow makes such a big difference, because it reveals some interesting aspects of natural gas that can be somewhat surprising. It ties back to the heating value of the various individual raw components that make up the mixture we call natural gas. The column on the left and the column on the right are both lists of the heating values for the various pure components shown in the center column. The thing to note is that when they are expressed in units of energy per unit mass, all of these heating values are very similar. Contrast this with the large differences in the heating values of the same components when they are expressed in units of energy per unit of standard volume. Direct mass measurement of gas with changing composition is a more accurate way to measure energy for this reason. To really appreciate the magnitude of this difference in practical terms, consider the two example compositions shown. The total energy content of the two compositions would only change by 1.9% if you were to take two samples of equal size as measured by mass. But the total energy content of the two compositions would change by 9.9% between two samples if they were taken of equal size as measured by standard volume. This comparison helps to explain why the improvements in efficiency and emissions were so dramatic in the combustion control application, where the micromotion Coriolis meter was installed and used to control based on mass units. So let's pause again for a moment and take another poll question. How are you all using measurement devices to currently measure natural gas? There are several different meter technologies listed here, and I would appreciate it if you would all pick the one technology that is the most commonly used for your custody transfer measurement in your systems today. Please remember to click Submit when you're ready, as you did for the last poll question. Okay, and looks like we're getting some pretty good response here. I'm going to share the results with everyone now. So you can see there's a growing use of Coriolis meters at about 9%, but as I would have expected, differential pressure is by far the most common. And the obvious reason for that is because differential pressure meters and orifice meters have been used longer than any other technology. They're very well understood and are basically the de facto standard and have been for many, many years. The other thing that you'll note is that ultrasonic meters are very commonly used. Ultrasonic meters are quite popular in natural gas custody transfer, and Coriolis meters and ultrasonic meters are both growing in use in today's environment. And you can see ultrasonic meters have almost caught up with differential pressure meters, at least in this poll, in their popularity. So thank you all for sharing your answers with us on that last question. And with that, I'd like to move on to discuss the calibration options. One other big advantage of Micromotion Elite Coriolis meters is that they have the ability to be calibrated on water for natural gas custody transfer service. This is described in AGA report number 11, which instructs us on how to measure natural gas with Coriolis meters. However, AGA 11 is clear that it is only allowed when the manufacturer has demonstrated that the Coriolis meter design in question will measure natural gas accurately after calibration on another fluid like water. Micromotion has completed the testing required to demonstrate this for Elite meters, and this is well documented. The reason that calibration fluid flexibility is valuable is because it opens the door to allow meters to be placed directly into natural gas custody transfer measurement applications straight from the manufacturer's factory with no delays or additional costs associated with having to first send the meters to a third-party gas calibration lab. Even though it's possible to bypass a gas lab calibration altogether, if one is desired, it can and often is the case that operators will still choose to invest in a gas calibration by sending the meters to a gas lab. In fact, for customers that wish to apply the standard practice they use for calibrating ultrasonic gas meters in third-party gas labs now, micromotion meters may now be ordered with a software option that allows the gas lab to apply a multi-point piecewise linearization, commonly referred to as PWL adjustment. That is identical to the adjustment method used for ultrasonic meters. Anyone interested in using this optional feature should contact Micromotion to learn more about the steps they can take to follow this approach, and we'll be sharing contact information at the end of this webinar so you could reach me directly. This graph shows the minimum accuracy requirements for Coriolis meter measuring natural gas that comes straight from AGA 11. There's a basic minimum requirement of plus or minus 0.7% accuracy in the range of flow rates above the Q sub T flow rate. Below Q sub T, the meter accuracy requirements become wider. I'm showing this chart to explain that Micromotion Elite meters, which have a manufacturer's published accuracy specification on gas of plus or minus 0.35%, will be better than the AGA 11 minimum requirements by a factor of 2 or more. When placed into gas measurement service following the factory calibration on water, Elite meters will meet the published plus or minus 0.35% specification and without the need for a gas calibration at a third-party lab. At the same time, however, I can share with you that some customers have achieved agreement on the order of plus or minus 0.1% between the meter and the laboratory reference standards after applying the optional PWL adjustment. The traceability uncertainty of the meter measurement can never be better than the uncertainty of the reference standard that's used to calibrate it, so we recommend paying close attention to the uncertainty statements of third-party gas labs as you consider your options for calibration. However, with the flexibility and adjustment methods that are now available with the addition of the PWL option, it is possible to match gas lab reference standards very closely, and this will facilitate both meters and labs to continue to deliver better and better uncertainty in measurement results over time. We'll now talk about the tools that are available for field verification and maintenance. The most important adjustment to a Coriolis meter during calibration is the flow calibration factor, which adjusts the span of the measurement. But there is another adjustment that is as important in some gas applications where the range of flow rates will be wide. This is known as the meter zero adjustment. So if you think back to the phase shift between the two pickoff coils I talked about earlier and the proportional relationship between that and the mass flow rate, you can imagine that relationship as a straight line like the one shown on this graph. The equation for a line is m times x plus b, where b is the intercept, or the point where the line crosses the phase shift axis when the mass flow rate x value is equal to 0. The term m in the equation is the slope of the line, and it defines how much phase shift is equal to a certain amount of flow rate. So the meter zero adjustment is the way to eliminate the measurement error due to meter zero, or b, in the equation. And the flow calibration factor that's set at the factory is the parameter that is set to establish the slope of the line, or the span relationship between the phase shift and the raw pickoff signals, that is the mass flow rate. As the actual meter zero varies, the line will move up and down, but without changing slope. Notice how the error as a percentage of the flow rate only changes a little bit at the higher mass flow rates when the zero varies, but the error as a percentage of flow rate will increase more and more as the true flow rate gets closer and closer to zero itself. Compare that to the effect of the change in the meter span, or flow calibration factor. This will cause the slope of the line to change as shown. Variation in the flow factor will have a large effect on the accuracy of the flow rate measurement across the entire range of flow rates. So both the flow calibration factor and the meter zero are carefully adjusted on every micromotion meter during factory calibration. Micromotion recommends using the flow calibration factor and the zero factor that were set at the factory in all applications unless there is some evidence that an adjustment to either or both factors will improve measurement accuracy. The Micromotion provides the tools that can be used to check the flow calibration factor and the zero value of the meter after it has been installed to find out before making any changes if the adjustment might improve the measurement accuracy. I will describe the tool for checking the zero first, and we'll get to the tool for checking the flow calibration factor after that. In order to use the diagnostic tool that can check the meter zero, it is first necessary to fully stop any flow through the meter. It is also extremely important to make sure that the meter is completely full of the right fluid with no bubbles or condensate present. This is important because condensate flowing down the walls of the flow tube or bubbles rising in a liquid will appear as actual mass flow during the diagnostic check, and it will yield bad results. Similarly, the process conditions, including pressure and temperature, should be made as stable as possible for the zero test. Once the required no flow conditions have been established, the next step is to initiate the Micromotion meter zero verification test. This test runs automatically and will tell you in roughly a minute whether or not the process is stable enough to verify whether the zero is good or not, and it will then tell you whether the current zero setting is good. If one of the multiple diagnostic measurements that are run during the test indicates that the conditions are not stable enough for a conclusive result, the tool will give you advice as to what you need to remedy the problem. Conversely, if everything looks good and the zero is good, it will advise you to leave the zero setting alone. One final note, it is always possible to restore the original factory zero setting from where it is stored as a record in memory in case the zero adjustment is ever made by mistake in the field while the conditions are not stable enough. So as we discussed earlier, the flow calibration factor is the most important parameter to ensure the best flow measurement accuracy over the widest range of flow rates. For that reason, Micromotion has developed a highly sophisticated tool for checking it called Smart Meter Verification, or SMV for short. The Smart Meter Verification method falls into a category of secondary verification techniques that do not go as far as checking against a traceable flow reference standard, but they do perform a meaningful check of a secondary meter attribute that is known to correlate reliably with the primary flow calibration. Similar techniques that are used with other technologies as secondary verifications would include physical inspection or miking of an orifice plate, spin-down tests on turbine meters, and profile symmetry checking in multipath ultrasonic meters. So AGA 11 acknowledges that valid secondary verification methods may be used to bolster measurement confidence of Coriolis meters in natural gas applications. The potential benefits of having the ability to perform an in-situ check to confirm the accuracy of a Coriolis meter include reducing system losses and better system balance, a reduced chance of prior period adjustments that will result from undetected measurement shift, a low-cost method for checking each meter more frequently, and the potential to extend the interval between expensive primary calibration events with greater confidence. You may be wondering what secondary attribute of a Coriolis meter is the best thing to observe as a diagnostic to confirm that the meter calibration has not changed. The answer is the stiffness of the flow tubes. So a Coriolis meter is very much like a simple spring mass system, where the flow tubes are like the spring and the fluid inside the tubes is like the mass. When we use a Coriolis meter to measure flow, we are observing the combined effects of both the mass of the gas flowing and the stiffness of the tubes. If we could be sure that the stiffness of the tubes has not changed, then the only thing left that could be the cause of any phase shift or twisting of the tubes that we measure will be due to the actual flow, and we can rest assured that the calibration of the meter has not changed. Micromotion has developed a way to use sophisticated modal analysis of the sine wave signals coming from the pickoff coils to determine from the tube vibrations what the stiffness of the tubes is without any influence from the fluid that is inside the meter. This is an extremely useful diagnostic tool because it allows us to confirm that the meter is sound and that the calibration is unchanged easily and without having to remove the meter or compare it to any reference standard other than the internal recording of the original factory stiffness baseline measurement. The original factory stiffness baseline is recorded at the time of the factory calibration, where the meter is first calibrated against traceable flow reference standards. The SMV diagnostic tool provides a comprehensive print-ready report for your quality records that includes not just the results of the important flow tube stiffness test, but also includes other pertinent data, including a record of the integrity of the meter parameter configurations and the process conditions at the time of the test, as well as the health of the electronics of the meter and every other secondary diagnostic check that is performed simultaneously. The SMV diagnostic tool allows you to check the calibration of the meter in situ, and it could not be easier because it does not require you to do anything before running the test. You don't need to interrupt the flow or control process conditions. The flow measurement from the meter itself is not even interrupted by this process. Compared to the method that requires you to periodically shut down, remove the meter from the line, and send it to another location for calibration, SMV allows you to do more frequent testing while your process continues to run. It improves safety by preventing you from having to send someone into the field, and it avoids breaking seals in the gas line. Once SMV has been purchased and installed as part of the meter, there are no additional costs to run a test, so you can run as many tests as you want, as often as you want, without incurring any additional cost. I should pause here and remind everyone that Coriolis meters are extremely unlikely to be damaged in service, so the expected results of the SMV test are almost always passing with no change in the stiffness of the meter flow tubes. It's only in the rare event of corrosion due to incompatibility between the fluid and the steel of the meter. Most meters are built from stainless steel, but they're available in many different materials of construction. Erosion due to high velocity flow with an abrasive fluid, or severe overpressurization to the point of yield that would cause a stiffness change in the tubes. These problems are easily avoided with proper meter selection, sizing, and operation. As we conclude the webinar, I hope that you have come to the realization that with revolutionary micromotion Coriolis meter technology and Emerson as your measurement partner, you can achieve better system balance and measurement accuracy than what you have now, and with no flow conditioning. Micromotion meters are very simple to use because they measure mass directly, so pressure and temperature do not play any role in determining the total amount of the mass, or the standard volume, or the energy flowing. Think of the savings in real estate when each new meter run doesn't have to include 3 to 4 times the space just to meet the straight run requirements, and it doesn't require you to find more time in your day to come on site to repair the meter because it failed or drifted. With the combination of innovative technologies and field experience that we alone offer, we look forward to helping you improve your bottom line. Thank you for attending this webinar, and thank you for sharing your responses on the 2 poll questions especially. At this time, I'll turn it back over to Allison to lead the question and answer session.
Thank you so much for all this great information and for the great webinar. And thank you, everybody, as Mark mentioned, for your great participation in the surveys. We are now opening up for questions. We actually have many already flowing in here. So please use that chat panel to type in the questions, and Mark will kind of jump in and start answering the questions.
Okay, thank you, Allison. I'm just going to read some of these questions. Trying to start at the beginning here. Oh, can I measure in units of energy with a Coriolis meter? And we did actually cover the equations from AGA 11 and AGA 8 that will enable you to do that. And I just want to reiterate that the pressure and temperature are not needed in order to convert from the mass flow measurement of the Coriolis meter into direct energy. What is required is a gas chromatograph or some other way of determining the heating value, which is the amount of energy per unit mass or the amount of energy per unit of standard volume. let's see. Another question here is, can a micromotion Coriolis meter indicate when there's wet gas in the line? And yes, we talked about how Coriolis meters can be diagnostic for the process, as well as reporting diagnostic information on the health of the meter. The Coriolis meters can actually use continuous density measurement and also a measure of the amount of power that's being consumed to keep the tubes vibrating as a very clear indication of when there's moisture in the gas. And so it's a very good indicator of when your gas dips below the dew point or when you have wet gas passing through the meter. Let's see. So one question here was, what are the advantages of a Coriolis over an ultrasonic for natural gas custody transfer applications? And I think we touched on a few of these during the presentation. The biggest advantages I think that people are really keying in on are the ease of use and the simplicity of installation and operation. So I mentioned a couple of times during the presentation how simple the installation is because there's no straight run requirements. And I've been out to sites where the metering station piping comes right up out of the ground into the Coriolis meter and then back underground. And when you're trying to install metering stations in areas where you may not have real estate already, you can actually install a metering run with a lot less square footage using a Coriolis meter than with an ultrasonic meter or an orifice for that matter that will require you to have a straight run above ground. The other advantages are that the ultrasonic meters do require pressure and temperature measurement in order to take the ultrasonic reading and convert it to standard volume. So your basic standard volume measurement does depend on changing pressure and temperature. In addition, any other ultrasonic measurement that you take, you still need a gas chromatograph measurement of the composition and the heating value in order to get to energy units. So you don't really gain anything by having an ultrasonic meter in terms of being able to not have to worry about composition. Here's a question about the piecewise linearization. Somebody asked, can any gas lab perform the piecewise linearization? And I'm glad this question was asked because Micromotion has invested in working with some specific labs in North America to provide them with tools and training to program and configure the piecewise linearization. And I'll name these labs. The Colorado Engineering Experiment Station, CZ, the Southwest Research Institute, and TransCanada have all performed these types of calibrations. What is the maximum design pressure for Coriolis meters? There are actually certain sizes that have higher pressure designs, but the standard design for Coriolis meters is up to 100 bar pressure rating, or 1,450 psi roughly. Another question is, what is the smallest flow tube that we have? We manufacture Coriolis meters that range in size from 12 to 14 inch pipelines all the way down to 1/10 of an inch. So we get down into fractional pipeline sizes that are so small that the line size becomes more or less meaningless, and we start looking into pressure drop calculations. This is a good time to mention that when you're sizing a Coriolis meter, it's always a good idea to use the available sizing tools to program in your fluid properties, and this is true for both liquids and gases, in order to predict both the pressure drop through the meter, but also to predict the velocity through the meter. So a Coriolis meter can often be installed in a line where the cross-sectional diameter of the flow area through the meter is smaller than the total cross-sectional area of the pipeline that it's installed in. And when this happens, the velocity will speed up through the flow meter, and our sizing tools will tell you exactly what that velocity is. So you can be aware of that when you're doing your sizing. Somebody asked about rangeability of Coriolis meters, and that's a very good question, especially when you get into the smaller meter line sizes. As I mentioned, the smaller the meter is, the more likely it is to be used at a city or an industry gate. The larger meters are more often found in transmission lines where the flow rate is much more stable, more constant. But in general, the type of Coriolis meter that you choose will determine the answer to your question of how good the rangeability is. And it's very important, and this is why we recommend using our elite meters, because when I was talking about the signal-to-noise ratio and the importance of tube geometry, I touched on this, but the tube geometry gives you much more flow signal, and this is very important for gas flow measurement especially, because when you're measuring gas flow, you're at much lower density than you are when you're measuring liquid flow, and so the mass flow measurement through the meter is generally lower than it would be if you were pumping liquid through that same size meter. For that reason, both the flow signal and the zero stability are very important, and you get better rangeability with the elite meters than you do with our F-series meters, which have a shorter tube geometry. Okay, I have a question here. This is a good question. How does the meter measure density? When I want a volumetric value for the meter, is the meter dividing and calculating by mass to calculate the density? This is a very important question to consider for gas in particular, because it's easy to become confused here. The meter, a Coriolis meter can measure liquid density very well by just measuring the change in the natural frequency of the tube. So when you measure liquid volume, you can measure the volume of that liquid as an actual volume by constantly dividing the mass flow rate by the density. And that gives you the instantaneous actual volume, but that's only good for liquids, because the density of gas is much more difficult to measure. And it's very important here to also draw a distinction between actual volume and standard volume. So when you're measuring standard volume with a Coriolis meter, you do not use the meter density measurement. Instead, you use the density at base conditions. And as I talked about on the slide where we discussed the calculations from AGA standards, the base density for the gas is derived entirely from the composition. So from your gas chromatograph, you can get a base density or density at reference conditions that you want to use as a constant. The Coriolis meter allows you to program that value into the meter, and it will report standard volume using that base density value, but it's dividing by that constant rather than dividing by the live density value that it uses for liquid volume flow measurement. So very different answer depending on whether it's liquid or gas. Here's another question. Can calibrations be done in the field, or does the Coriolis have to be removed and sent to a qualified lab? Coriolis meters can be calibrated in the field. Usually this involves a master meter or some kind of traveling reference. However, with gas flow measurement, this can be more challenging because you need to be sure that you have stable conditions and that the mass or the standard volume flowing through the reference standard is the same as the volume flowing through, the quantity flowing through the meter that's under test. So it's much more frequent that you'll see Coriolis meters and any other type of gas meter pulled out of the line and sent back to a calibration lab for that reason, where conditions can be controlled. But it can and is often done that calibration against a master meter in a gas situation is done. On the liquid side, Coriolis meters are often calibrated in situ against provers. But that's a bit of a different situation. The question is about what range of flow and pressure are available for Coriolis meters, and can you get a catalog? Yes, I would encourage you actually to go to our online store, and you can visit that by starting at the www.micromotion.com website, and you'll find a link to the online store there. You can also access our catalogs, and that'll tell you all the different flow rate ranges and pressures that are available for different size Coriolis meters. And in addition, it gives you access to the online sizing tool, so you can see the effect of pressure and temperature and flow rate on the pressure drop and the velocity through the meter, and that can aid you in selecting between multiple different sizes that might be suitable for any application. Okay, somebody asked, which is preferred, the water calibration or the piecewise linearization calibration? This is a really good question because some of you may recall I mentioned early on that Coriolis meters are really linear to start with, so you may wonder why we have a linearization feature. And the answer is that the Coriolis meter is perfectly suitable for gas custody transfer, and as I mentioned, it can better than double the accuracy that's required as a minimum accuracy in AGA 11. So recall that the Elite meter gas performance is better than 0.35%, where really plus or minus 0.7% is all that's required as a minimum. So if your goals are around ease of startup and cost, you can avoid the cost and the time delays of having to do a third-party gas calibration by just installing the meter with a water calibration. However, we are definitely working together with customers who have a different set of priorities, and especially in transmission lines, we want to achieve better system balance. So if your priorities lean towards greater accuracy, it can be worthwhile to try and work together with third-party labs to improve on the accuracy of the meter even above what you get from the micromotion water calibration. And we are seeing some customers achieve on the order of 0.1%. So it's all a question of whether your particular installation and application provides justification for the added investment that's required to get you from 0.35% to 0.1% accuracy. One question we received was, what would be the percentage cost difference between a Coriolis meter and a Daniel Senior Sonic installation? And I'll just generalize and say, the cost difference between a Coriolis meter and an ultrasonic meter and a gas custody transfer obviously is something you'd want to compare at a detailed level, but I would say they're reasonably close. And one thing you definitely do not want to leave out of the equation when you do compare is the entire cost of the installation, including the straight run flow conditioning, conditioning plates, and real estate that's necessary for all of that you do need with an ultrasonic meter, but that you don't need with a Coriolis meter. So when you take all of those things into consideration, typically a Coriolis meter will be lower in cost than an ultrasonic meter installation. And don't also forget to include the cost of the calibration and transportation for calibration service as well. How are we doing on time, Ellen?
We are actually over time, and we still got questions coming in. So I think I'm actually going to call it. I realize we haven't got through all the questions. So if we haven't answered your question, don't worry. We will actually email you the answers to your questions post-webinar. So we'll get all of those, and we really appreciate all the participation. I mean, we've had a huge volume of questions still coming in. So we're really excited to have so many people engaged on this topic. We thank Marc very much for all this excellent information. So again, if we haven't answered your question, don't worry, we will, through email, answer your question. If you have additional questions after the webinar, again, don't hesitate to email Marc directly. His email address is at the end of the presentation, or there's the email button on the bottom of your console that you can contact us at. Also, at the end of the webinar, when you close out, there will be that survey that will pop up, so we would love your feedback to help us optimize the future webinars. We again thank you everyone for joining us. We will be emailing out a link to the recording of this webinar. It'll be Monday after the weekend, along with some links to additional resources and how you can get superior accuracy of your natural gas measurement. Again, on behalf of our guest, Marc Buttler, as well as everyone at Emerson Micromotion, we thank you all for joining us today on your Friday and taking time to not only view the presentation, but provide us some great questions and interaction. We hope you all have a great day and great weekend. And again, we will be following up on Monday with a link to the webinar. Thank you very much.
Yes, thank you very, very much.